Good morning, everyone. My name is Ryan Eveler. These are my team members, Dan Taylor, Christian Peterson, and Connor Michelini. And we are the representatives for Breakfast Inc., the Pancake printing team. And this is our final oral progress report. So a brief outline of our presentation today. First, Dan and I will talk about the design process and some of the decisions that we made throughout the last 2 semesters, both mechanically and electrically. After that, Christian will go into the building process and how we actually manufactured and assembled our final system. Connor will then talk about the final design and the results of that, along with the testing that we did to ensure that we met the criteria specified in our SDRD. And then Connor will talk about some reflections that we made, both things that we would change in our system if we had been given more time or more money, and also the things that we learned throughout this process. And at the end, as always, I'll open up the floor for any questions you may have. So our overall design is consisted of 4 main subsystems. These subsystems are the image conversion process, the batter extrusion subsystem, the trolley movement subsystem, and the user interface subsystem. The first one, the image conversion protocol, is how we go from a specified user image and convert that into the code necessary for our system to communicate with itself. The workflow goes as such. You begin with uploading an image to Inkscape or drawing your own image inside of Inkscape. Inkscape is an open source vector imaging software that we chose because it's open source and there are a lot of tutorials online that you can use to learn the program. After you have uploaded an image, there are extensions built into Inkscape that allow you to export a G-code file. The G-code file contains a set of coordinates and movements that specify a toolpath, which then we can take that file and upload it into a parser. This parser is one that we created ourselves that takes all the necessary information out of that G-code file. It generates Python commands then and compiles all those Python commands into a single file. This single file then can be opened up inside of our user interface on our Raspberry Pi and is what is used primarily for the system to communicate the movements for the motors. The second subsystem that I'm going to talk about is the batter dispensing subsystem. So the batter dispensing subsystem has multiple components, including a single one-directional DC air pump, 2 3-way valves, and a batter hopper. And the batter hopper is just a repurposed ketchup bottle that we used. So there are 2 main requirements that the batter extrusion subsystem had to fulfill. The first, it needed to be able to extrude batter onto the griddle at multiple speeds. Along with that, it needed to be able to suspend the batter inside the hopper and prevent it from dripping onto the griddle. In order to accomplish these 2 requirements, we utilized the 2 3-way valves to reconfigure the air movement inside the system. So in the first setup, we can configure the 2 3-way valves like this, and when turning on the DC air pump, we draw air in from atmosphere, goes through the DC air pump and towards the backside of the batter, extruding the batter onto the griddle. The second configuration is in order to suspend the batter, and by changing the configuration of the 2 3-way valves, we can now draw air from behind the batter, creating a vacuum and suspending the batter there, and then we expel that air out towards the atmosphere. The third subsystem that I'm going to talk about is the trolley movement subsystem. This subsystem contains 2 stepper motors, a series of timing belts and pulleys, along with shafts and bushings that allow for the movement of the trolley, and along with a motor hat. And the motor hat is pretty much just a motor controller that is attachable to the top of our Raspberry Pi. I'll now hand it off to Dan, who will talk more about the electrical aspects of our subsystems.
So I'm going to talk a little bit about the controls. So we chose the Raspberry Pi as our controller for a few reasons. One, because it's open source, so there's a lot of support out on the interweb to help you learn about it. Also, it used Python as its main programming language, and it has several peripherals, and you can just plug an HDMI cable into it and plug it into a monitor and start coding right away on it. So that was really nice because right when you get it, you can pretty much start coding the motors, and you can start creating a graphical user interface. It's pretty much just a plug-and-play sort of situation. The I/O pins, there's a lot of I/O pins. It also provides a PWM pin, and it provides a couple I2C pins, which I'll talk a little more about later. And then for our motor driver, we used the Adafruit motor hat. This one was really great because it came with a library of motor functions. So we were able to use those in our own functions that we made. This is also a good driver option because you can control multiple motors with it with just using this one hat. This is because of the ECE interface. And it also is great because it just stacked right on top of the Pi, so it was relatively easy to connect. And all of the pins that it stacked on top of were also made available on the hat, so it was like easy to access them. So here's a couple, some of the functions that we made. The biggest function that we made was the vector move to function, which basically took in coordinates from a text file and then performed some calculations on them and would move the extruder over the griddle to the specified spots for a design layer or for a fill layer that we were doing. And then we had this limit XY. This was a really important one because we were experiencing a little bit of drift with our trolley system, and it wouldn't always be exactly where we wanted. So this function basically would zero out the trolley system using limit switches. It would run it all the way to the limit switches in the zero out coordinate system. And then this turn off motors is kind of a simple one. It basically just releases all the coils on the stepper motors so that they don't get really hot, which I accidentally left them on a couple times and forgot to use this function. They got really warm. So these are for some extrusion commands, and all the variables in these are pretty simple. The pump may seem a little confusing, but that's just an object referencing the PWM pin. The turn battery on, that just extrudes the battery. You just give it rate of speed and the pin number, and then change battery speed. This is nice because then you can change battery speed on the fly. And then we have turn the battery off. This is actually not turning off the pump. This is creating back pressure inside of the ketchup bottle so that we can not be dripping batter all over the griddle. Next I'm going to talk about some GUI integration. So this is just kind of an aesthetic page of the graphical user interface. We use tkinter, which is a package in Python that comes standard with Python to create graphical user interfaces, which actually at first it seemed like it would be a simple thing, but there were some complications because of the way that it renders these windows. And so it has a loop basically, and it's constantly looping through to update the window. And when you're trying to run like motors, things like that, those executions, they run in loops too, and they take time. And so the window isn't actually able to render an update while you're running like a motor file or while you're trying to do other things simultaneously. So we ended up doing some parallel processing, which wasn't super hard to implement. We had to do parallel processing for the timers especially. You can see the timers right here. They've got some buttons with them. Basically, the workflow of this is you click the browse button, which is right here, and then you'll be taken to a browsing window. You select your files. After you've done that, you'll fill up this like file queue area so you can see what files you're going to print. And then basically how this works, you go through, you do each print, you print each design, and then once each design is printed and it's like sufficiently cooked, then the trolley will go all the way back to the beginning and it'll do the fill layer for each one, and the timers will start after the fill layers are completed. So once these fill layers are completed and the timers have told you that it's now time to flip the pancake, then you would click this flip button and then each next button subsequently telling the controller that it's time to move on to the next phase of the timing to click the other side. A piezo buzzer beeps when your time is up for cooking a side or when you've finished cooking pancakes. And I'll pass it off to Christian, who will talk about construction.
So for the more physical side of the construction, there was numerous things we needed to do as within a project. But first off, we needed to print all our 3D printed parts. And this ended up being a little more painful than we originally anticipated, just because either there'd be some random error with the printer or just the tolerances and the dimensions that we gave the printer ended up being not quite exactly what we needed. And when moving around the trolley, we kind of needed to be as precise as possible to help get accurate dimensions on our designs. We also had stock that served as our guide rails for our trolley system as well as supports, and so we had to cut those to length. And all while we were doing this, each time we got something new basically printed or cut, it was installed onto the HDPE base. There was also the circuitry that needed to be made, and so that was done. I mean, they weren't exceptionally complicated, but regardless, they needed to be done. And those are all tucked away into the big red box that's on the left side of our HDPE base, which I'll talk about in a moment. But then, as Dan kind of, or not Dan, whatever. The batter consistency was another big issue that we kind of needed to focus on, because as you may have seen in our demonstration, the batter consistency has a huge effect on the performance of our system. And so we did spend a little bit of time on that. And so throughout the design process, we were constantly thinking about just protecting the system from batter and all that, and as well as making sure that it looked good and the user could access things that they needed to access, such as the hose that they connect back to the air pump, as well as the user interface, which would be sitting right up front. And so the air pump right here is one of those things. The only thing that the user will be able to access readily would be the hose that goes at the top, which is connected to the black connector you see at the very top right of the box there. And so the user will be able to easily do that. But everything else, the air pump, the hoses, the valves, and the motor, they're all in here so that, one, they're protected from batter, like I said. But then if something goes wrong, it is easily accessible for the user, and they can fix it. But then as far as circuitry goes, we wanted to make sure that outside of the air pump box, circuits weren't all everywhere, so the user, one, couldn't damage them. Then they could also get in the way of the printing action. So that's something we need to take into account. So we put it's all in the big red box over there, and that houses everything from our Pi to the touchscreen, as you see right there, as well as numerous other things, such as the hat and our proto board that we have all our circuits wired to. So as far as aesthetics goes, the user will easily walk up and realize I need to plug in the user interface, and that's what I'm using to control the Pancake printer. So there were numerous bugs along the way, as with any coding. So one of these major ones was fixing the motor movement command. Originally we had something where we were threading the two motors to move in 1 volt motion, X and the Y would be moving at the same time. But we put in a command for saying the X move in 200 steps and the Y would move in 300 steps, like in this picture. But unfortunately, due to some issue I don't think we were never able to fully understand, we were getting a print that was more like the middle. And so obviously that's not something we want when we're printing. And so instead of using the commands, we did a one-step command, which moves the motors one step at a time and creates a bunch of smaller movements that when you scale it back down to how far it goes, you get a straight line. And that actually made our prints very consistent and our designs very consistent. Another small issue we were having was controlling the air pump. Sometimes on initializing the code, the air pump wouldn't turn on, or sometimes while we were printing, the pump was for some reason not working or something like that. So we do have a button in the GUI to toggle whether or not the pump is on or off, mainly just to make sure the pump is in reverse flow, just to make sure that you're not dripping better everywhere. And then as Dan kind of alluded to earlier, we were having some issues with drifting. And so in order to alleviate that, we zeroed out the Pancake printer after each print. Yeah, for each design, we went and zeroed it out, and after each fill, we went and zeroed it out. And so that alleviated a majority of our drifting issues. So now I'll pass it off to Connor, who's going to talk about the performance of our system.
So pictured here, you see our final product of our system. Once we had it all built, we wanted to move on to testing it and making sure we were meeting all the expectations we set forth in our SDRD. To do this, we have kind of 3 main tests for our printer. The first being the user interface test, which deals with everything the user will be interacting with our system. The second is the printing and cooking test, which deals with laying out the pancake design and then cooking it and removing it from the griddle. And finally, we have our out-of-box inspection test, which is kind of the aesthetics and the weight and dimensions of our system. So in the user interface test, the requirements we're looking to meet here are we wanted to have a single button to initiate the printing once you had loaded up the file queue. Secondly, we wanted to make sure we had at least 3 preset designs to run from our Pancake printer. For our purposes, it was a smiley face, the Valpo shield, and a star. We wanted to make sure you could queue up at least 6 pancakes, that way you don't have to do one pancake run. And lastly, we wanted to make sure that the temperature of our screen never exceeded 100 degrees Fahrenheit, just to make sure it's safe for the user to use. So pictured here, we have our current iteration of our GUI. Underneath the browse button, you can see we have our single run button to, once you've loaded up the queue, you hit it and it begins printing the pancakes. Inside the file queue, you can see we have it loaded up with our 6 designs. These are based on our 3 preset images. And finally, we measured the temperature of our touch screen, and we are at about a max of 90.4 degrees, so well under our 100-degree mark. Moving on to the printing and cooking test. So what we're looking to make sure we do here is we wanted to make sure whatever design you were laying out only took less than a minute to lay. We wanted to make sure it never took longer than 8 minutes to do a single pancake. We wanted to make sure our pancakes were between about 4 and 7 inches. If they're too small, you're not going to be able to see your image very well, and if they're too big, you're not really going to get to enjoy the pancake. We also want to make sure we alert the user when they need to flip and remove the pancake. And lastly, we wanted to make sure our resolution was at least a ½ inch. So the results of this test, the max time we found for laying out any of our 3 preset designs was about 22 seconds. This is well under our minute mark. Next we checked, so the longest time we had for a single pancake of printing, laying down the fill layer, flipping, and removing was 4 minutes and 42 seconds, which is also well under our 8 minutes. Next, our pancake sizes generally vary from about 4.5 inches to 6 inches. This is very dependent on batter consistency. As far as alerting the user, we have a piezo buzzer inside our big red box, which will beep when you need to flip and remove the pancake. This is coupled with an on-screen notification telling you which pancake you should be doing and which action it is. And then we measured the line thickness of our designs, and they were about a quarter inch. So the out-of-box inspection test, what we're looking to check here is that all of the parts that come in contact with the batter and food that anyone think will be consumed were food grade. The only parts of this for our system are the griddle and the bottle, and both of these are up to that standard. We wanted to make sure our printer fit within these dimensions you see on the screen, just so that it could fit on a general size countertop. We are within each of them for all 3. And lastly, we wanted to make sure our printer weighed less than 40 pounds, just so that it was feasible for one person to lift and move the printer. For our purposes, we measured the system, and it was about 25 pounds. So some improvements we would make if we had more time or money. We'd like to nail down kind of a consistent batter recipe. As you saw during our final demonstration, it's really important. If it's really runny, you get kind of the big mess you saw. It also helps with laying down the actual image. Moving on, we would probably add encoders to our motors. We do have a bit of a drift problem sometimes, so it will go and lay the design layer, zero out, and come back to do the fill, and not be quite at the same center. So being able to know exactly where we are with our motors would be important. Lastly, we'd probably like to invest in a more precise drivetrain system to also, again, help with this drift, maybe a screw drive, just to get a better idea of where we need the printer to be. Lastly, some lessons learned over this senior design experience. Obviously, time and money are kind of a big thing. With more time and money, obviously, you can make a better system, buy better parts, get things better. Proper distribution of work among team members. We had a bit of a problem first semester with kind of some people had a lot to do and some people had very little, so being able to properly distribute that from early on would have helped. Kind of going along with that, parallel workflows. We did have a bit of a bottlenecking issue this semester where most of the mechanical system was up and running, but we were kind of waiting on the programming graphical user interface to kind of get going through. And lastly, communication. So we had a bit of an issue this semester with communication between the mechanical team and the electrical team, solely on the purpose of the GUI, where some of our mechanical members came and said, okay, here are some functions we'd like to have in the user interface. And the electrical team had already had the user interface done, so we vetoed many of those ideas. So in summary, Ryan and Dan talked a little bit about our design process. Christian went over the build. I went over our final testing and design, and a reflection of our senior design experience. Are there any questions?
I think you kind of run into a traditional problem you can sometimes see is that you have to control your material input, right? And it really affects your system. So I know you said you wanted better batter control. Doesn't the batter also change, like if you had the machine sitting there a couple hours, it may thicken? Like, what would be your ideas to keep that batter consistent?
So the question was, what are some better ideas for keeping the batter consistent? And we had talked for a while about having some type of way to set like you have the user be able to set the speeds of the pump based off of kind of how running their batter is. So have a calibration set up. So like you can just input any batter you want, and it would do a certain design, and based off the quality of that design, the user could just change some settings on the printer to have a better design output.
So let me see if I got this. You can optimize your parameters for a certain batter condition.
Yeah.
So why was the temperature of the screen one of the conditions you identified as being important? And what do you think is leading to this higher temperature than I might expect the screen to be?
So the question was, why did we think having the temperature of the touchscreen was an important thing to make sure of, and why was it slightly higher than you might expect? So we just wanted to make sure that anything the user was supposed to come in contact with wasn't dangerous. So we wanted to make sure they would be able to touch the screen and not injure themselves, obviously. And as far as the temperature of why it was higher than you might expect, I don't really have an answer for that. I know human bodies are around 98 degrees, I believe, so 90 is, I know it's dangerous. Any other questions?
In one of the slides you showed that initially you have a oblique motion and then you change to a zigzag motion. Did this affect your output, or would it look nicer if you had the oblique motion instead of the zigzag motion, or did it affect it at all?
So the question was about changing our motion from kind of just the oblique motion and instead replacing with lots of interchanging multiple steps. The issue I believe Christian tried to address with the big oblique motion was we didn't have quite the control of the motors when we tried to do it that way, which is why we switched to the kind of single step method. We didn't see any issues with using the single step method, and so since we weren't able to correct the speeds of the both motors while doing the oblique motion, we felt the single step worked better.
Thank you.